Good morning, everyone, and thank you for coming to this talk. My name is Furmanek, and for the next 60 minutes, we are going to talk a little bit about basic designs and how we got them wrong. We are going to see some fundamental concepts behind our programming languages, behind our platforms, behind .NET, JVM, and other languages as well. But the very important part that I'd like to start with is that during this talk, I'm not going to teach you anything that you would actually use tomorrow when you go to the office or on Monday. Actually, it's going to be even different. This talk will not change how you do stuff. This talk will only show you a couple of things, how they evolved, how they are broken, and maybe one day how they will be fixed. But I'm not going to teach you or to show you how to do things differently, unfortunately. That is because we are talking about basics and about things that are very behind all the things that we are using every day. What's more important, even though, is that during this talk, I will ask you to forget what I told you. So this is something that we are yet to see. A couple words about myself before we move on. I'm a software engineer with 15 years of experience now, author of these 2 books. Drop me a line on email, Twitter, visit my blog at blog.adamfurmanek.pl. At the very beginning of the slide deck, there was a QR code. The same QR code will be at the very end. It will point you to the slide deck if you would like to download it and check it out. Okay, so the agenda for today is we are going to go through a couple of basic principles, basic designs, basic things that were grounded and fundamentally impacted all the platforms, all the languages that we use today. We are going to bash those principles, we are going to see how we misunderstood them, and we are also going to show how they are broken and wrong in many places. We'll start with things like Liskov substitution principle, then we'll go through a couple other things from Solid. We'll also talk about inheritance, and we are also going to talk about other stuff. This agenda, we probably won't cover all of that. That is because this talk is planned for something like 90 minutes, and we have only 60, so we'll do as much as possible. So let's jump straight to it. Liskov substitution principle. Hands up if you know this principle. Most of you. Hands up if you know how you broke this principle last week. Okay, and this is where things got tricky. Whenever we talk solid, we probably know single responsibility, open, closed, blah, blah, blah. You know the drill, right? And there comes Liskov substitution principle. What's that? Well, we have square, rectangle, we break it. We have apple, orange, fruits, whatever, we break it. How do we do that with abstract factory provider in C#, right? Where do we break it? Where is this principle even applicable? Do we use this principle at all? It's one of the most fundamental principles in Solid, and yet sometimes it feels like it's a little bit misty and we don't know what to do with it. So let's start from the very beginning. So Liskov substitution principle comes from a paper from 1994, the paper titled A Behavioral Notion of Subtyping. You can actually go and Google this paper. I mean, it's actually a pretty good thing in our domain, in IT, in computer science in general, that the people who actually build the foundations are still around. So you can go, you can meet Kent Beck, just like during this conference, you can meet other people, and you can actually talk to them about the things they wrote like 30 years back. It's kind of harder when it comes to maths, because we know all those great mathematicians are now long gone, but with computer science, it's easy. So we can go and Google this principle, Google the paper that proposed Liskov substitution principle. And it is important to understand what this paper tried to achieve. So we can read in this paper that this paper takes the position that the relationship should ensure that any property proved about supertype objects also holds for its subtype objects. What does it mean? Explain to me like I'm 5. The thing is, the authors of this paper wanted to say that, hey, we think this is a good idea, and we generally recommend that if it's possible to prove something about the supertype, then it also should hold for the subtype objects. We think this is good. This will lead to better designs. This is what they basically are telling us. They are not saying that, hey, this is like a law of nature. right? Nothing of that kind. It's just we think that it's a good idea. Now, what does it really mean for the property to hold? And if we go to examples showing how it works, we can, for instance, land on Wikipedia and find one common example about squares and rectangles. If you go and read what is Liskov substitution principle, you'll probably quite often find example like this one or similar with fruits, animals, or whatever else, right? So the example that we'll cover here is with squares and rectangles, and Wikipedia tells us that there is a square class, and that square class derives from a rectangle class, right? Nothing special here. So rectangle has two setters and getters. We have two sides. We can change the sides, width, and length. Nothing magical here. The square class, on the other hand, always assumes that the width is equal to height. So both sides are equal, where makes sense for a square, right? And now Wikipedia tells us that square, if we use it in a context where rectangle is expected, then we may break the LSP. That is because in square, we cannot change both sides independently. We can do that for the rectangle. We can change both sides independently. We can't do that for square, okay? And this breaks LSP. So far, so good. Let us actually now discuss this thingy. What if I wanted to implement a ratio-maintaining component? Imagine that we are implementing a framework for the UI code, widely popular framework, WPF for short. And in this WPF for short, we would like to have a component that basically keeps the ratio of an image, right? So as with every framework, you can imagine how those are implemented. We have some base class, base interface like iComponent or whatever, something we can put on a Canva. Right? This obviously must have some dimensions, width and height, right? That makes sense. So now I would like to create a component that maintains its ratio, so the ratio of the content inside, right? So let's say that now I would like to basically, what I want to do now is, if I make this component taller, then, well, it needs to be wider, because it needs to maintain ratio, right? Now, you tell me, does it break LSP? Hands up if you think it does. Okay, couple of hands in the air. Hands up if you think it does not. Okay, couple hands in the air. So now I ask you two questions. If this thingy does not break LSP, then why does this? Because those are exactly equivalent concepts here. And second thingy, if this does break LSP, then how do I implement this component? Because that's a real-life use case, right? I need to have this component maintaining ratio. How do I implement this piece so I don't break LSP? And those are two questions that are slightly harder to answer, but they will become clear once we get really into what this LSP is talking about. And just a spoiler, this doesn't break LSP. And let me explain you why. If we go into the paper from 1994, so 30 years back, we can see that this paper proposes an idea that if there is a property that in the paper they call phi of x, and if it's provable for the supertype, so we have some property that we can prove for the supertype, then we would like it to be provable for all the subtypes. That's the idea that, hey, the software will be better if we make it this way. And you can actually even see the quote, the screenshot from the paper itself. What does it mean in other words? In other words, we have something, we have a property that we can prove for the base class. Now we take the instance of the subclass, something that inherits from the base class, and we would like to also take this property and be able to prove it. Okay? That makes sense. The question is, what is a property? And if we take property as kind of anything, then we quickly run into this very fancy case that let's say that my property of the base class of the method foo on the screen is that the intermediate language, or actually not even an intermediate language, but the machine code of this method is just as you see on the bottom of the screen. That's my property. Can I prove it about the base type? Sure I can. Well, I just go, decompile it, deassemble the code. That's the property I have just proven. Now I would like to inherit from the base type, override the method, and I should be able to prove exactly the same property, the property telling me this is the exact machine code of the method. Does it make sense? it effectively blocks the polymorphism at all, because I can't override the method, I can't change the implementation, right? There is something wrong in this understanding. So what is wrong? The difference here is not all properties are worth being provable. And the important part here is LSP is about explicit contract, about properties that we specify explicitly. So we now have another word, contract. Let's ask what the contract is. And according to Wikipedia, you can go and figure out that this comes from 1986, 8 years before LSP paper. So probably the authors of LSP already knew about this concept, like contract. And we can read that design by contract is software designers should define formal, precise, verifiable interface specifications. So it needs to be formal, precise, and verifiable, right? We kinda know what this contract is. We learned design by contract. We know about invariants, preconditions, postconditions, yada, yada. And LSP is about the contract. So let's take the example of square and rectangle again. Typical example that we have is, again, square derives from rectangle. We have two setters for two sides. Square now breaks the LSP because we can change one side and it changes the other side at the same time, right? Does it break the LSP? No, because we never said that you cannot have this behavior. You never said that you have to be able to change both sides independently. That was never put in the contract. So that is the case, and that explains why the example with fixed ratio component also doesn't break LSP, because the I component interface at the very top does not require you to be able to set two sides independently. This is the contract, or actually lack of the contract. How can we change this example of squares and rectangles into something that actually breaks the LSP? Well, super simple. We need to explicitly say, when we define rectangle, that both sides must be changeable independently, right? We must be able to change those independently. If we do not say that explicitly, then there is no contract, according to the definition of design by contract. And this is what LSP is about. Okay, enough theory. How do we actually break that stuff in real world? Just to summarize, contracts must be explicit, precise, formal, verifiable. The problem with contracts in real life is that our source code, unfortunately, is not enough to define all the contracts that we are about. Many times we need to define contracts in wikis, documentation, in some architecture diagrams, even in organization like common style of coding. That also makes the contract that we should adhere to. And this is the problem. If we take languages like C#, how many of you are C# or .NET developers in general? Yeah, most of the room. So if we take C#, we may say C# is powerful, especially when we compare it to JavaScript or Python, right? We have types, we have classes, all is great, compiler protects us, right? But how do you, for instance, create a method that the compiler would make sure that the method accepts a list of, let's say, at least 2 elements? Can you do that in C#? And we are talking about compile time safety, not about runtime safety. You can obviously create your own at least 2 elements list, inherit from list, throw in the constructor, whatever else, right? That's not the point. The point here is, can we have compiler protect us from this mistake? And there are better languages in terms of the strength of the type safety that, for instance, can do that. There are languages like Haskell, like Scala, like Idris. They can do this magic. You can, for instance, specify that your list must be at least 2 elements long, right? Those things, and compiler will protect you from there. C# is still powerful language as compared to other of them, but still, we can't explain all the requirements in the source code, and that's why we need to resort to wikis, documentation, and whatever. And now, let's see how we break that in real life. So we are going to consider an example code that I saw once in like 4 different projects over 2 weeks. So that happens quite a lot. At least that's from my perception. And I believe you may have seen something similar in your code base as well. So let's see how we break LSP in real life. Let's say that we have a method that is called do with optional backup connection. What does it do? Let's say that we need to download a file from S3 bucket. right? And we have two different buckets, bucket A and bucket B. Like bucket B is backup or whatever, regionalized, whatever, right? So what we would like to do is we go to the first bucket and download the file. If it happens that it's not there for reasons, then we go to the other bucket and grab it from there, just as a backup, right? You can think the same situation like you have two different network interfaces, network connections. You go through your broadband. If it failed, then you go from your modem or mobile hotspot or whatever, right? That's the idea. So we have a method that is called do with optional backup connection, and this method basically takes two different clients and takes the lambda, expression, func, whatever, that will basically do the job with those clients. And the implementation that we have here is very simple. We try doing that with the first lambda. If it breaks and throws the exception, then we use the other connection, right? So the backup connection, okay? That's it. We have this helper method, and we would like to use this helper method to do some business code. So what do we want to do? Well, we would like to get the first file, the second file, the third file, concatenate them just for the sake of the example, and that's it, okay? That's our business code. I hope you get the idea. We basically download 3 files, and we just want to get from one bucket. If it fails, then from the other backup bucket, and that's it. How do we unit test this thingy? Because we are good developers, we test stuff before pushing to production, right? So we do it this way, and you can think about how you would test that, but I guess you might come up with something like this. So I have a test that basically is passing 2 different clients. One of the clients always throws the exception. The other client always succeeds, right? You take your Moku or whatever library and you do this magic, and you basically do the work and you assert that it equals to expected or whatever, okay? You push this to production, tests are green, all works well, people start to complain. Why? Well, they start to complain because if you take a look at this code, then what it does is it goes to all those files one by one. Serially, right? We download the first file, it takes half a second. Then we take the second file, another half a second, then another file. If we have thousands of files, it takes plenty of time. How do we make it faster? Well, notice that the author of this code was like pretty clever, we would say, and they designed this interface, client, that we can use to change the behavior, right? So what do? We change that to async, exactly. So we give that to our junior developer on the team because it's super simple, right? How do we change that? Well, we take the client, we basically change it to task of string that would be in C# or whatever promise of string we have here. Instead of just getting the result, we would do wait for result or await this thingy, yada, yada, and that's it. Nothing else changes, right? Because that's very mechanical change. So we have this. We now take a look at the unit test, see both clients, we run those unit tests, they are all green, we deploy to production, all is great, doesn't work. It breaks in production. Can you tell me why? And let me show you the implementation again. Just by doing this refactoring, let's call it, even though it's not refactoring, just by doing this change, changing this to async, I broke this whole mechanism. It doesn't work anymore. Any ideas why? Exception, that's a good direction. Okay, what we did is we broke the LSP here. If you remember how I was explaining this method, I told you that this method takes the first client and tries to do something with it. If it breaks and throws the exception, then it uses the second client. What happens if something breaks with async? Where is the exception propagated? The exception would be propagated in here, in the place where we would do the await, not in the internals of this whole call, right? So what we did now is we broke the LSP by changing the contract. The contract here was that if the client breaks, it must throw the exception. Now the exception is not thrown, it's stored on the task of string or whatever of string in our language, and the exception is propagated only in this line of code. This is how we broke LSP. And as I mentioned, I saw this issue in like 4 different projects over 2 weeks. Always the same case. Just make it asynchronous, give it to junior developer on your team. Super simple, doesn't work in production, okay? Now the question is, how can we prevent this from happening? How can we write a unit test that would spot that we broke the LSP, that we broke the contract in here? And the unit test we would need to write is actually pretty complex, because what we need to do is we need to verify whether the client throws the exception. It's not that we test whether our concatenation of strings works. What we need to do is we need to prepare the client to throw, and now depending on your client implementation, either you mock the internals, right, and you throw some weird exception when you access the network card, or you basically run this test with actual network connectivity and try to access in non-existent bucket. Right? So this makes it harder, but this is how we need to test for the contracts and how they break. So this is actually how we should prevent this case from happening. And hopefully when junior dev comes in and sees, okay, this is red after my changes, they do not break this test. They do not remove this test. That may also happen. Okay, let's carry on. So we mentioned LSP. It's about contracts. It's about contracts that are explicit, provable, verifiable. Question is, what can be in the contract? So if we actually now, let's bash some Java now. How about that? So if we go to collection.add in Java, so basically something like list of t in C#, if we go to the documentation of the add method, we can see that, well, first, it's a wall of text, which is sometimes good, but the interesting thing here is it may throw unsupported operation exception. How can you have a list of t, like you have one job to do, and you throw unsupported operation exception on me? Like, why? Okay, stop bashing Java, let's bash C#. C# does the same, by the way. Go to documentation. Now, why? Why? What's the case? The case is we would like to have immutable collections. For immutable collections, the add method either shouldn't exist or it kind of should throw, right? Because, well, for the immutable instance, we don't have much other choice. The question is, which is better, and what does it actually mean to have immutability? When we go out on the internet and we start Googling what is immutability, we can actually find two different definitions. People use the same word for two different concepts, even though the better naming was immutable and read-only. So what we have is, when we want to talk about immutability, we need to answer whether we are talking that we won't change something. So from our perspective, something will be just for read-only. We don't write, don't modify, don't do anything. That's first definition. Or second definition is nobody's gonna change it, ever. While it's easy to just make sure that it's read-only just for us. Like, for instance, if we don't have the add method, then obviously we won't modify it, right? So this is easy. We can prove it. It's super hard to prove that nobody's gonna change something. Why? Because first, we don't know what instance we are dealing with, and that's one of the pillars of object-oriented programming, right? We don't know what the instance is. We have polymorphism. Second thing, people know about hacks. Reflection, like memory pointers, other things. It's super hard to actually prove that nobody's gonna change it. And third, and the worst is, we don't even have access to the code that would be dealing with that. We might be loading code dynamically from third-party dependency or whatever, and we can never prove what it's gonna do because we don't have this code. So now the question is, what should we do and how should we implement immutable collections? And if we go to Java, let's come back to Java for a sec, they explain in their documentation why they decided to have add method on the collection, and this method can throw the exception. I actually encourage you to go and read this wall of text explaining what's going on behind the scenes. That is because obviously C# was copycatting Java a lot, and this is only one of the examples where C# cloned Java, so we have exactly the same explanation why it happens in C#, okay? So I encourage you to take a read. But there are other languages running on JVM. You probably heard about Kotlin, about Scala. What do they do in order to provide immutability? So if you take Kotlin, you do have immutable collections, right? How do they work? Well, we have two different interfaces that inherit from exactly the same root. So we have iterable, that's something like IEnumerable in our case. We have iCollection, and then we have iList, iSet, IMap, that would be iDictionary, basically, in our case, right? And then we have mutable counterparts, and notice that mutable list inherits both from list and from mutable collection, right? So now, when we talk about immutability in Kotlin, what we are talking about exactly is I get the collection that I can't change. If I specify that I want to get a parameter that is of type list, then I can't change it. But I have no idea whether it's actually like a list or a mutable list, right? However, if we go to Scala, Scala decided to do it differently. How do they do it? They have two completely independent class hierarchies. One class hierarchy, the one on the left, is the thingy that is immutable. So those things never change unless someone really goes and does tons of hacking behind the scenes, right? With low-level, crazy reflection and pointers and whatever, right? And the collection on the right, or the hierarchy on the right, is about classes that can change. So notice what is important in here, that we have the same names, we have the same names both here. For instance, we have map that is mutable, and we have the same thingy here, map that is immutable. They live in two different namespaces, have exactly the same names, but live in two different packages, as they call it. So that's how we explain, how we express whether we would like to have immutability or read-only collections. Similar case in C#, right? In C# we do have read-only collections. We do have read-only like types that express the idea, and the idea is much more closer to this Kotlin thingy, not to this Scala thingy. Okay. Enough of that. So we finished LSP. Solid is quite beautiful, have many principles. Let's bash dependency inversion now for a second, okay? What about dependency inversion? Let's say that I would like to change, or actually let's start with this question. How do you replace a string? We are C# developers. We have our system.string, or wherever it lives. It has some implementation. You probably know the implementation is based on array of characters, right? Each character is how many bytes long? 2 bytes long, right? Why? Because we copied from Java, and Java wanted to have characters that can express UTF-16 code set. We know it doesn't work anymore because UTF-16 is actually 21 bits long, so 2 bytes kind of doesn't work for this case. But that's history. So we have characters, array of characters. Now, what strings do we typically deal with? Obviously, American ones, right? So we have ANSI strings or ASCII character set or whatever else, right? How many characters do we have there? Something like 130 with some special characters, but generally less than 8 bits for storing all of them, right? What happens now? I have a string that wastes like half of the memory for storing those additional bytes that we very rarely use, if ever, right? Now the question is, how do I replace this string? How do I change the implementation of the string? And if you go actually to GitHub, you will find that .NET wanted to do that. There are some types like UTF-8 string type that is kind of going towards this direction. Now, can we do it in the source code? Can we change our strings to be UTF-8 based instead of UTF-16, so basically with characters? And obviously, if you dig deeper, you know that it's not possible. Why? First, because the string class is a class. It's not an interface, right? And have you ever actually thought there is an interface for string, something like iStringable? We don't have that, right? Second, it's a sealed class, so we can't inherit from it and change the behavior. Third, internals of .NET Runtime heavily rely on the string implementation just because they grab a pointer and go through the characters with low-level magic. So if we change that implementation, we change .NET Runtime and break it heavily. And the other thing is, even in intermediate language, we have string literals. So it's basically like a first-type, first-class citizen, we could call, something living on its own, representing a string. String implementation is so deep into the .NET runtime then it's kind of hard to change it. But you might ask, okay, why would we ever change it then? I know it's a waste of memory, but hey, we have terabytes of RAM now, so who would care, right? So let's see some history. In Java, for instance, they implemented it the same way, or it's the opposite. We implemented it in the same way. And around Java 9, they changed this implementation. So now they have strings that can switch the implementation between like 2 bytes for a character versus 1 byte for a character to save the memory. They also changed the concatenation performance. Just because we do the plus operator and join two strings, and it's compiled to something, in Java, it uses the instruction that is called invoke dynamic that creates a specific call site after you start the application. So the first execution is slow, but then it's super hard. It's very similar to DLR, dynamic keyword that we have in C#. First execution is slow, but once we have all the call sites, it gets much faster. So they did it. They did it in Java. What else? Facebook, they decided to change the implementation of their strings in C++. I actually encourage you to take a look at this talk that is titled The Strange Details of STD String at Facebook. And they explained how they changed the implementation and achieved 1% performance improvement. And you may say 1%, is it worth it, right? But when we think about scale and we think about hundreds of thousands of machines they have at Facebook or at Meta, then 1% is actually a big chunk of money that we can save just by doing that. And the way they did it is they just replaced what string you import after they implemented it. If we take a look at JavaScript, for instance, we typically say that an object in JavaScript is basically a dictionary, a hash map, right? So we have a key and a value. Arrays are represented the same way. Basically, a key is a number, right? 0, 1, 2, whatever, and then a value, right? But if we take a look at how it's implemented in V8, then there are 5 different implementations, or at some point there were at least 5 different implementations that were tuned for particular performance. So if you have an object that is like only 2 keys and 2 values, that's it, then we store it differently to save memory and also to improve the performance of read and write access. So we want to do those hacks. Actually, if you ever go to any like fancy talks these days about .NET and you hear about span, memory, about array pools and all that stuff, they always brag about, hey, notice we just changed the implementation, you now get slice, it's turbo fast, right? They just do it this way. They exactly do those things behind the scenes. Can we change the string? Well, we cannot. That is the case. We broke it, and if you take a look at solid principles, dependency inversion, you should never code against implementation. You should code against interface. Is string an interface? Not at all. It's class, it's sealed class, it's exposed on so many levels. Generally, we can't do that, right? But that's not the end of the story when it comes to string. If you have datetime now, do we have an interface for getting now? Now we do. How many years it took us to finally get the interface for datetime now, right? For the things from static configuration, right? That was mostly historical. Those things hopefully successfully changed. Environment exit. Do we have something like iExitable interface? If you ever call environment.exit directly in your code, think twice. I encourage you, because then one day on Friday night you wake up and why is my application dying with no reason? And then you figure out someone called environment.exit. So always have an interface and generally always block this method. Do not do it without logging, but that's another thingy. What's more, it's not enough that we broke those principles like dependency inversion. We even figure out a way to test how we broke it. For instance, most libraries, for instance, power mock in Java, for instance, other mocking techniques to mock static, to mock private, to mock other things hidden behind the scenes, right? We know how to deal with that even though we just break the principles. That's the thingy we are doing wrong. But we can take it even further. Imagine that Adam Furmanek would like to create a new language, better C#, make C# great again, and Adam Furmanek decided that this fancy language will have colors of a function. Every function should be either green or red.
That's cool. You just need to specify. Just like you specify method is void, return string, whatever, we specify that it's green function or red function. So far, so good. But then I tell you that, hey, if you have two green functions, you can call them easily. If you have green function that you would like to call from red function, it's kind of OK. Let's do it. If you have red function called from red function, all is good. But if you have red function called from green function, nah, that doesn't work. Don't do it. What would you think about a language like that? And now, does it resemble you anything? Yeah, it does. It's exactly what we have with async. Async in C# is exactly called function coloring. So we have functions of two different colors. And if we call a synchronous method from a synchronous one, that's a big no-no. And if you were around 10 years ago when they introduced async and you had to rewrite all your synchronous code bases to asynchronous ones, and you wanted to really cut corners and change synchronization context and do all the magic to avoid rewriting these tons of code, and you hit all the deadlocks, you know what I'm talking about. But that's not the end of the story. Now we have value task. It's even better. You shouldn't be calling value task from a task because, well, it kind of is against the purpose, right? Notice what we are doing here. And I actually have even other talk that is titled Async biggest mistake in C#, so I encourage you to take a look at that. But what I'm saying here is we broke dependency inversion heavily because now every function that we have needs to know what it does and how it does it. It needs to know whether it is returning a regular task or a value task. It just needs to know that this breaks dependency inversion, this breaks SRP, this breaks so many principles. And all the languages, they copied it from C#. So Python, JavaScript, C++, all the languages, they went this way and just copied it. The only language that did it in different way was Java. Go was actually doing it in the same way, I think, as C#. OK, so we bash Java, we bash other languages. Let's carry on. Do not repeat yourself, right? OK, so let's see another example how we break decent principles in software engineering. And actually, let's mock async just a little bit more. You know that you shouldn't be calling async functions from synchronous ones, right? So this is if you ever call file.readAllText, right? You can go behind the scenes and you see that it kind of does this. Makes sense, right? So we basically make sure that our parameters are correct. We get the stream reader, read the file, no magic here. How do we do that in async? Well, in async, things are getting a little bit trickier. And the important thing to notice here is first, this is way longer. Second, much harder to understand what's going on. And third, you just can't reuse implementation between those two methods. You can't take synchronous code and call it from an asynchronous one. It will technically work. You won't have any deadlocks, right? But it will be too slow. It will completely break the concept of asynchronous programming. So what do we have to do? We need to implement every method async, every single method async. I'm just waiting for console write line async. And honestly, I'm like serious here. Because I've seen a single project in which console write line was actually a bottleneck. Why? Because console write line synchronizes access to the console window, right? So console write line async makes sense. Hopefully one day we're gonna see it. So async actually defeats the purpose of do not repeat yourself. Fortunately, we have a completely different principle nowadays. I don't know whether you have heard about it. It's called wet. Write everything twice. That makes sense. Let's carry on, folks. Inheritance. And here comes Reagans. If I ask you, do we have multiple inheritance in C#? Hands up if you say no. OK. Hands up if you say yes. OK. Hands up if you just failed the interview question for a C# developer. Gotcha. OK. This is a common question. Do we have a multiple inheritance in C#, right? Common question during C# interviews, yada, 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 yada. The answer typically shouldn't be surprising, but as we already know during this talk, it's not as easy as it may seem. The answer is no. We don't have multiple inheritance in C#. That was the correct answer. But now we can actually ask, do we? Do we? Is it really the case? So typically we can inherit only from one base class. This is the case in C#, this is the case in Java, this is the case in many other enterprise-ish language these days, right? Sometimes we can't even inherit at all. Let's take structures in C#. Can they inherit? Well, if you read the internals, you know they inherit from something like a value object, I think that's called, then which in turn inherits from system.object, but you can't make structure inherit from another structure. Why? Just because. That's the answer. They just made the decision that you can't inherit one structure from the other, even though technically it's perfectly possible. Probably could make some issues if we really take edge cases, yada yada, but generally should work pretty well. So this is what we say. We only have single inheritance in C#, in Java, in those languages. But actually, let's dig deeper. So multiple inheritance was a feature of object-oriented programming in which we can inherit from two base classes, right? C++ allowed us to do so, and it posed a problem that we call a diamond problem. The problem where we inherit from two different code paths, and it kind of makes things shaky. So we have class A, and this class A is a base type for two different classes. Sorry, my mouse is gone, and oh, there it is. So we have base class, and then we inherit from it with two subclasses B and C, and then we have D. And now if D would like to access some field or method from A, the question is, should it go through B or should it go through C? And this is a problem that we typically call a diamond problem, as you can see from the shape. And this problem was so important in C++ that Java decided, no, we are not going this way. We ban multiple inheritance. We don't make it even optional. It's prohibited. This solves the problems for good. C# was copying from Java, so we have exactly the same. Now, what I'm going to show you in the next slides is that first, not only do we have diamond problem in C# and in Java, we had it from the very beginning and we solved it in many, many places. So let's see what's the case. We solved the diamond problems many times. Let's take some C#-ish code. Let's say that we have interface A with method void foo, and then we have interface B with method void foo, and then we have class C that inherits or implements A and B. And notice this subtle difference now. Java was so scared of multiple inheritance that they even renamed the activity we do when we inherit from interfaces. We implement interfaces. We do not inherit from interfaces. That's a subtle difference. So we implement two different interfaces, and we provide method void foo, and then we do this. So cc equals new cc.foo. Is it going to compile? Hands up. Yes? Yes? No? Okay, so the answer is yes, it's going to compile, and yes, it's going to work. Why? You may say there is no diamond problem at all in here because, well, those two methods, they have exactly the same signature, right? It's the same name, the same list of parameters, the same return type, no diamond problem at all, okay? Let's make it a little bit more interesting. So another C# riddle. I have method foo that accepts two integer parameters, and then I have method foo that accepts an array, which is a params array, so ellipsis array, and I do this. Is it going to compile? If yes, hands up. If no, hands up. Okay, the answer is yes, it is going to compile. Which method is it going to call? The one at the top, hands up. The one at the bottom, hands up. Okay, the answer is it's going to call the one at the top. It is going to compile. It is going to call this method at the top. Why? You may say, well, no diamond problem at all. It's trivial here, right? We have two parameters. This method has two parameters. Makes sense to call this one over this one, right? This one is just pretending that it has two parameters or many, right? But notice another important thingy. What if this method doesn't exist? This code will compile and will work. What happens if we then introduce this method? We break the backwards compatibility on the execution level. Why? Because the code still compiles, right? But now it calls a different method. Okay, But that's edge case, nothing special here. We have two parameters versus one parameter, all makes sense, no diamond problems, no fuzzing around. Let's take another riddle. We have a method foo that accepts long, and we have a method foo that accepts double, and then we call it this way. Notice that 1, 2, 3 is neither long nor double. It's neither of these two. Is it going to compile, and which method is it going to run? And you may say, well, it's obvious. 1, 2, 3 is long or double? OK, long, hands up. Double, hands up. OK, long was more common. That probably makes sense here. It's obvious that 1, 2, 3 is long, right? That's how we solved the diamond problem in this case. Again, notice that if we didn't have this method, and then we introduced it, then we, again, break the compatibility, right? But here, C# authors, they decided, obviously, 1, 2, 3 is a long integer, not a double, even though it could work for both cases. Let's take it even further. We have two interfaces. One has method object foo, the other has method string foo. We implement two interfaces, and then we implement the method with string foo. Should it compile? Will it compile? And I guess you have some hint on the slide. Will it compile? And now, why? And this is interesting because the same code will compile in Java. This won't work in C#. In Java, it will compile. Why? Because they decided to support this feature. They decided to support this, and they implement it via the so-called bridged methods. So they have bridge methods that will actually, behind the scenes, will take the string foo and will call the object foo when you have the different instance that you would like to call, actually, OK? C# decided this is something we don't support. And you may now say, it actually makes sense, right? Another diamond problem where we made some arbitrary decision, and we can argue whether it makes sense or not. As I was trying to, convey the message, it can be clear and obvious here what the decision to make. Can be clear and obvious here what the decision to make. Can be clear and obvious what the decision to make here. What about this one? So we have two interfaces, interface A with default interface implementation, and then interface B with default interface implementation. Both of them, they have the same void foo method. We create class C that implements both A and B, and we call c.foo. Is it going to compile? Hands up. OK? So is it going to call method from at the top, hands up, or at the bottom, hands up? And I can see no one is raising their hands now, OK? What is the answer? It's not going to compile. Why? Because we have a diamond problem. But how to make it compile? Where to make it compile, it's actually super simple. What we need to do is we basically need to do something like sys equals new C, and then we cast the C to the proper interface and call foo. And bang, it works. You can tell me now, how is it different from the actual multiple inheritance with this case? And obviously, we can argue whether it is different, whether it's the same. But let's carry on those discussions. Diamond problem happens in many places in programming languages. It's not about the inheritance per se. This is how we typically think about the diamond problem, right? But it's not the only case. It's about that we have the same thingy that can point to two different things. So the same piece of code that can point to two different things, and we need to decide, OK, we need to resolve to which thing it does point. Okay? And there are many ways to do so. We can say that nobody decides. We simply ban such a code and assume that it doesn't exist. We can say that there is just one logical peak, so we just make this peak, just like with this void foo method in interfaces, right? We can say that there are many peaks, just like with methods accepting longs or doubles, and we just make the decision just because we know better. Or we can ask the user to make the choice, just like we have with the multiple inheritance in this case of default interface implementations. And we solved the diamond problem in many places already. It's not that we need to be scared of this problem. It's just we can solve it. We need to be just explicit how we solve it. But let us now go to the multiple inheritance question in C#. Actually, there are different types of inheritance if we take a look from a theoretical point of view. So we have signature inheritance, implementation, and other. Let's see them one by one. Signature inheritance is when we inherit the interface, the set of method signatures or method declarations, right? So we basically, a method signature in C#, it's the name, it's the list of parameters, and that's it. Return type is not a part of the method signature in C#. Interestingly enough, it is a part of a signature in the intermediate language. If you start writing code in the intermediate language, in IL, then you need to specify the return type of the method when you call the method, because you need to be very explicit, because you need to make the choice and resolve how to call it. In C++, it's actually even more interesting, obviously, because C++ is just more interesting when we need to deal with details. And in this case, when we talk about signature inheritance, we do have multiple signature inheritance in C#, because we can implement multiple interfaces. Right? So we do have multiple signature inheritance. Another type of inheritance is implementation inheritance. In implementation inheritance, we inherit method bodies. Not only the signatures, but also the bodies of the methods. And we can see now that we have that in C# by the default interface implementation. So we do have multiple implementation inheritance in C#. When it comes to state inheritance, we inherit fields of the classes. And this is something we do not have in C#. We can't inherit fields from multiple classes, but since we can inherit multiple bodies, thanks to implementation inheritance, nothing stops us from pretending like we are inheriting fields by implementing a static concurrent dictionary that would keep the body of all the fields that we are into, and this is how we could implement multiple state inheritance, but C# doesn't support that according to the definition. And finally, identity inheritance. In identity inheritance, we inherit the constructor of the type. Again, in C#, we do not have this feature. We don't have multiple identity inheritance in C#. Or do we? And let me actually show you a little bit of code that is actually doing some, let's call it black magic. So we create an object, multiple inheritance object. Let's make it a little bit bigger so for you to see. And we basically create multiple inheritance instance that inherits from all those base classes, right? What are those base classes? If we scroll down, we have base class with like integer field, with byte field, with like doubles, with string, whatever. And they all have different methods like print string, print fields, print byte, print int. Okay? So we create an object. Notice it's important here, this is an object, okay? What we do then is we print the address of this object, and then we try to take the object, multiple inheritance object, and we would like to pretend it's now base 1. So we take it as base 1, and you can see it's base 1 here. We get the type of this thingy, we get the address, we assign field, and then we call a method. We do the same for base 2. Notice that we take base 1 object, so the one that was initially multiple inheritance object here. We take base 2, we take base 2 as base 3, we take base 3 as base 4, then as base 3, and whatnot. And if we take it, you can see that, what do we have here? Well, the address of this object is always the same. The content of this object is changing, and obviously, the type of this object is changing. So if you really want to have multiple inheritance, you can take a look at this piece of code. So now coming back to the slides, let me ask you this question at the very end of the day. Is there a multiple inheritance in C#? Hands up if you say yes. And now forget what I told you, because you will fail an C# interview question. The answer is no. Let's carry on. We have a couple more minutes, so we will just wrap it up with exceptions. Exceptions are always great to deal with. That is because we always pretend like it's all going to work well, and then obviously it fails. So exceptions. Trivia question, yet another one. Let's see that we have the following C# code. So we have try, then we have finally, and we catch some exceptions. So in try block, we throw the exception 1, okay? Then what happens is we would like to handle this exception. So we start analyzing the code with two-pass exception system, and we notice, oh, there is a catch handler. So we should handle this exception, right? So we start unwinding the stack. And then in the finally block, we throw exception 2. Now the question is, what's going to happen? What exception do we get in this catch block? Exception 1, exception 2, exception I have no idea what I'm talking about. What's going to happen? Is it going to blow out? So the important thing, before actually answering the question whether this code actually happens in real life, the very important thingy about C# is that if you ever have a code, if you ever have a code that would not have this exception handler here, so you wouldn't have this drop, try, catch, then this finally block is legally allowed to not be executed. This is something that C# specification tells you, and there were some runtimes that were actually not executing this finally block. This is important because such an unhandled exception, first, it may kill your application because just one unhandled exception kills your entire process. That's not very reliable, but that's for some another time. But second, this is actually allowed that you won't run those finallys, and those finallys may be important. Why? Because you may need to release system-wide mutexes, release cloud logs, or whatever else, right? So always have a top try-catch. Always. That's a rule of thumb that applies to C# and all the languages you can think of. Always have try-catch. And now, let's discuss this example. So we have two nested tries. Someone is throwing in finally. That doesn't seem like a good idea. We would obviously stop that during code review, right? It just happened that we have such a code. Is it going to break anything, and what's going to happen? And now, where do we have this code in C#? And we actually have this code in C# in many places. And those many places is, if you ever run using construct in C#, then what happens? Notice that this code is compiled to this piece of code. So you take this initialization and you put it before this try block. Okay, so notice that if there is an exception thrown in the constructor, I know, yet another stupid idea, we don't do that, although there are some people that are actually hitting the database from their constructors because they do domain-driven design and they always want to have the entity in correct state. Yes, some people hate that, some people love that. Let's not discuss that. Generally, if the exception is thrown, it happens before try. It's worth to remember that. But what happens here? Well, if there is an exception thrown, then, well, obviously, we would like to handle this exception. Imagine there is a try-catch block, but notice there is not. It may be that this exception will never be caught, so the finally will never be executed, and this is perfectly fine. But imagine there is a try-catch block here, so we execute finally. What do we do in finally? We call resource dispose. What happens if resource.dispose throws the exception? We have exactly this problem. By the way, using is broken in C#. Do not use this construct. We'll get to a solution in a sec. So finally, let's answer the question, what happens in this scenario? And it heavily depends. C# will lose the first exception. So what you are going to have in here is exception 2. You will lose exception 1. You won't be able to recover it easily. Other languages, depends. Python may lose the exception, may keep the exception depending on the version. Java may happen the same depending on the exception type. Actually, in C#, depending on the exception type, this catch handler may not be executed at all. That also makes things a little bit more complex. So generally, it is crazy. How should we fix it? Well, to fix it in C#, this is the piece of code that you should instead of the using construct. So what do? Well, we prepare two variables for exceptions. We initialize the thingy before the try block just for the sake of compatibility with the using construct. We throw the exception, we catch the exception here, and then in the finally block, we try to dispose the resource, we catch the other exception, and then we basically do some ifology to figure out whether we had one exception or two of them, in which order, and ultimately we just throw the exception. But you might ask, hey, Adam, why are you doing this crazy magic instead of just throw, right? What does throw do? How do we rethrow exceptions? Well, if we take a method that, like we have this piece of code that is calling those two methods, then we catch the exception and we would like to rethrow it here. How do we do that? Well, you probably know that if you do throw E, then it's a big no-no in C# because we lose the exception stack trace, okay? That's a big no-no. We have a special dedicated instruction for that. That instruction is throw semicolon. And this should propagate the exception stack trace properly. There is a problem, though. You will lose whether the exception was originally coming from the line at the top or from the line at the bottom. Throw semicolon is broken. Trademark period, do not use it. What should you do then? Well, if you are unlucky enough, and you, for instance, run .NET Framework very old, then you do not have magic that was introduced later on. But this magic basically is you can use exception dispatch info throw. That is a construct, that is an instruction that was added to support async scenarios in which we had to propagate the stack traces properly between async calls. So you can use this instruction to pre-throw the exception properly. If you don't have that because you are running .NET Framework version 2, anyone in the room doing that? Good. I won't need to mention that many times anymore. Then you could do some other magic, for instance, tricks with remoting or whatever else. And one last thing, actually, let's call it finally. We say that finally should be executed no matter what, every single time. We obviously know this is not true because if you just unplug your machine, there is no option to execute finally, right? So let's not do that. But there are many other situations in which finally may not be executed at all. And just be aware of that. It may be skipped when your application simply terminates by doing environment exit or whatever. Why? Because there is a time limit for those finallys. If they are too long, they won't be executed. They may be ignored depending on the exception type that you try to catch. They may be skipped on unhandled exceptions, as I already mentioned. And finally, may swallow exceptions. And this is also important. So whenever you have to throw an exception, make sure that you deal properly with logs and with whatever stuff you have over there. That would be it, and we'll need to skip the rest of it. So summary. Many things that we use, they are just broken. That is somewhat because it's history. That is somewhat because we just didn't follow the best practices. That is because we just decided it's better, or that's how it works. So remember about those things and just be aware of those. Remember about the contracts. That is the most important part I want to stress here. Liskov substitution principle and generally all the programming is about dealing with the integration layers, right? Think about the contracts, make them explicit. Remember that they may not be entirely in the source code. They may be in wikis, documentation, agreed over the phone with your client. Those are the best contracts that we are afraid to touch for the next 10 years. So generally, be aware of those. Beware of async. No matter how it sounds in C#, you should be aware of async. And that would be basically it. If you happen to have any questions, it's the right time to ask them. At the very end of this slide deck, there are some links that you could take a look at to read more. This QR code points you to the slide deck if you would like to download it. And being all of that said, I'd like to thank you for coming to this talk. Hope you enjoyed it. Thank you.